In this video, we're going to see how to set up ice tables for more complex equilibrium type of problems that incorporate stoichiometry. So we're not really going to solve the ice tables just yet. In the first few examples, we're just going to set them up. An ice table is a table that allows you to keep track of concentrations from the beginning of a reaction all the way up until you reach equilibrium. So here we have a system that can reach equilibrium. We have SO3 plus H2O gives you H2SO4, and we're told that your initial concentrations of SO3 and H2O are 1 molar and 2 molar over here. And so we're going to set up an ice table in order to keep track of the concentrations of the various substances in the reaction over time until it reaches equilibrium. So on the top row, we're going to write the reaction out. So SO3 gas plus H2O gas, then our double arrow there, H2SO4 gas. And in the first column, we're going to put units of molarity, which just basically means mole per liter. And we write ice along the table, which means initial concentration, change in concentration, and then concentration at equilibrium. So an ICE table. And in the initial concentration portion, we'll put the initial concentration of each substance as given. 1.0 molar here, 2.0 molar over here. I don't have to write molar or mole per liter because I wrote it up here, and that's fine. Now, what about the product? Well, assuming that this is a mixture at the beginning where there's no product at all, you only have reactant, your product concentration should be 0 because you haven't produced any yet. So these are initial concentrations. You haven't produced any product yet. You only have reactants. The change is based on the molar coefficients, on the coefficients in the balanced equation. So for each reactant, you're going to be losing some because they're being consumed. And so basically we're going to have minus x. If there was another coefficient in front, like a 2, we'd put minus 2x, or a 3 minus 3x. This one's also minus x. And then for the product, since we're making some, it should be plus x. And again, if there was a coefficient in the front other than 1, you'd replace the 1 in front by that number. So for the overall concentration at equilibrium, you're simply going to have 1.0 minus x. Over here, it's 2.0 minus x. And over here, it's x. So what that means is that over time, you started off with 1.0 and you lose x. And so your new concentration will be whatever 1 minus whatever x is. And then H2O, you started off with 2.0. Over time, you lose x, and your new concentration will be 2 minus whatever x is. And then for H2SO4, it'll be, you start off with 0, you gain x over time, so your new concentration will be x. And later on, we'll learn how to solve for x, but right now, we just need to know how to set up an ice table like this. So try this example yourself first, and then afterwards, you can check your work by taking a look at the video. Here we have another system that could head towards equilibrium. We see that with the double arrow. We'll set up our equation at the top. 2H2 gas plus O2 gas produces 2H2O gas. Over here, we'll put our molarity. And actually, in this case, it's not molarity. If we read the question carefully, it's actually pressure in ATM. And the reason we can use pressure in ATM is because remember that relationship PV is equal to nRT. So as pressure goes up, so the number of moles, they're directly related to each other. So we can put our pressure in ATM and keep track of the equilibrium that way as well. So here we're going to put our initial pressure, which is 0.66 ATM for H2 and 1.28 ATM for O2 and 0 for H2O. Notice the coefficient in front of the H2 is 2, so we're going to lose it, but it's minus 2x rather than x. In front of oxygen, it's 1, so minus x. And in front of this H2O, it's 2, so plus 2x in this case because we're making H2O. So our final pressure at equilibrium is simply going to be our initial, take away the 2x. For the O2, it's our initial, take away the x. And then for our H2O, it's simply 2x. So what we've done in these two examples, we've set up two ice tables. We didn't really do any work with it other than setting up the ice tables. Now we'll go a step further. We'll be able to figure out the K value given some additional information and using an ice table. So here we have a system that can head towards equilibrium. Temperature is given to you because remember that the equilibrium constant can be affected by temperature since it's a rate or since it's a ratio of rates. And so we want to write out our reaction. So this is our reactant. There's our arrows. We have H2. We have I2. Our initial concentration, we need to be careful here, and you can pay close attention here. Notice we have 0.7 moles of HI, and it's in a 2-liter vessel. Now, the 0.70 moles is not concentration. Remember, concentration is in moles per liter. So we have to do C is equal to N over V, which is equal to 0.70 over 2.0 liters moles, which is 0.35 molar. And assuming that we didn't have anything else in the reactant vessel, this should be 0 and this should be 0. Change in concentration, well, we're losing HI over time with a coefficient to 2, so minus 2x. And then we're gaining the other with a coefficient of 1 each, plus x and plus x. So our concentration at equilibrium is going to be here 0.35 minus 2x, and then here x and x. Now, here we have some additional information given to us. It says calculate K if the equilibrium molarity is I2 is 0.060 mole per liter. So the equilibrium concentration of I2, which we said was x, is actually equal to 0.060 molar. And since H2 is also x, that should be the same equilibrium concentration, 0.060 molar. We can actually also figure out the concentration of HI at equilibrium, so 0.35 minus 2 times 0.060, and you get, so you do your 2 times 0.060, 0.23. Now in this question, you're asked to figure out what K is. So our step one was really establish the ice table to find the equilibrium concentrations. And why do we need those? Because remember that K is going to be your equilibrium expression. And we're going to plug these values into the equilibrium expression. So we have our products multiplied by each other, all with an exponent of 1 because they have coefficients of 1, over the reactant with an exponent of 2. And now we can plug these numbers in. So we'll have 0.060 times 0.060 over 0.23 squared. And we should get, let's see, 0.060 times 0.060 divided by 0.23 squared. 0.0680529.3. Remember, no need for units because K units vary quite a bit, so we don't include them. And we want to round this to the correct number of sig figs, which is 2 sig figs. In this case, that's the smallest number of sig figs we have. So about 0.068. This is our K value. So what we just did here was we set up an ice table in order to find the equilibrium constant. To do that, we have to be given some information, such as one of the equilibrium concentrations, and then from there we can figure out all the rest. So we're given this x value over here. In the next video, we're going to see a similar situation where we're not given the x value. Instead, we're going to be given the k value, unlike here. Here we have to find the k value, and we're going to have to find the x value. So it'll be a very similar situation, except the difference is we'll know k, and we'll have to isolate and solve for x instead. And then once we have x, we can go and find all the equilibrium concentrations. It's a bit more involved, and sometimes there's different strategies you'll have to use, but it's as simple as just making an ice table, making an expression for the equilibrium constant, and then solving for x, and then plugging in x into each one of the concentration formulas that you made at equilibrium. And that we'll see in the next video, which will be example 6. Before you watch the next video, you may as well try the problem out yourself to see if you can solve it. And if you do solve it, check your work with the video. If you can't solve it, go watch the video fully and then retry it until you can solve it without any issues.